YouTube viewers. It's Crystal here, and in this video what we're going to talk about is a few ways that we can make estimations in statistics, and we're going to use the R programming language to actually make those estimations. So the first method of estimation that we're going to carry out is the method of moments. So the method of moments involves equating simple sample moments, e.g. a sample mean or a sample variance, to population moments and solving for the parameter estimates. This method is straightforward but may not always provide efficient estimates. So we're going to use the R programming language to demonstrate the method of moments. So the first thing that we're going to do is we're going to set our seed. And the reason why you set your seed is so every time you run the program, the variables will be initialized to the same value. And then we're going to generate sample data from the gamma distribution. And so we're going to create the variables k and theta. So your true k becomes 3. That's your shape. And your true theta becomes 2. That's your scale. So we're going to create the gamma distribution, which is going to be randomly sampled. So x becomes r gamma, brackets 500, so that's 500 samples, comma, shape equals true k, and scale equals true theta. So now what we're going to do is we're going to sample the moments. So M1 becomes mean x, that's your first sample moment, and M2 becomes mean x squared, and that's your second sample moment. It's being a little bit awkward. Okay, so then what we're going to do is we're going to method of moments formulas for the gamma distribution is EX equals K times theta, and EX squared equals K times K plus 1 times theta squared. So now we're going to solve for K and theta using sample moments. Theta hat becomes M1 minus M1 squared divided by M1, and K hat becomes M1 divided by theta hat. And then so now we've got theta hat and K hat. So your theta hat is 1.7247, and your K hat is 3.3277 because we printed that out. And now we're going to plot a histogram and the method of moments fitted density. So the hist brackets x, comma, breaks equals 30, frequency equals false, color equals light blue, border equals white, main, which is your title, is method of moments fit to gamma distribution. XLab is your label on your x-axis is x. Now you're going to add the density curve. So curve brackets d gamma. So d gamma means it's the density of the gamma distribution. Brackets x, comma, shape equals k hat, scale equals theta hat, comma, add equals true, color equals red, line width equals 3. We're going to add a true density curve for comparison. So curve brackets d gamma brackets x comma shape equals true k, scale equals true theta, add equals true, color equals dark green, line width equals 2, LTY equals 2. And then we're going to add a legend. So your legend brackets top right, comma, legend is going to be paste method of moments k, and it's going to be around k hat 2, comma, theta equals around theta hat 2, comma, and then paste brackets true k equals true k, comma, theta equals true theta. Color equals red and dark green. So red corresponds to the method of moments and dark green corresponds to the true. And then line width equals C, that's creating a vector, C comma 2, and then LTY equals C comma 1 comma 2, and BTY equals N. And then so you over here, you've got your true K is a dashed line. So what they've done is they made the method of moments just a straight line, which is red, and the true K is a dashed line, which is green, dashed. Okay, so now we're using the gamma distribution, and the gamma distribution, the shape of the gamma distribution is going to change depending upon what your K is and what your theta is. So the method of moments for K is K equals 3.33 and theta equals 1.72. And then the true is K equals 3, theta equals 2. So we come over here. So you can see here the true K, we made that 3, and we made the theta 2. And you can change the K and the theta, and the K and the theta will change the shape of the gamma distribution. And so what you can do is you can experiment with the K and the theta to change the shape of the gamma distribution so you can see how that works. So the next thing we have is we have the maximum likelihood estimation. So the maximum likelihood estimation involves finding the parameter values that maximize the likelihood function, which measures the probability of the observed sample given the parameter values. Maximum likelihood estimation is widely used due to its desirable properties, such as consistency and asymptotic normality. Maximum likelihood estimation, we're going to have a demonstration of how to carry out maximum likelihood demonstration in R. So the first thing that you want to do is you want to set your seed. So set dot seed brackets 1, 2, 3, and what that does is every time you run the program, the variables will be initialized to the same value. And now we're going to generate sample data from an exponential distribution. So your true number becomes 0.2, and your x becomes REXP. So REXP means a randomly sampled exponential distribution, brackets 100, that's your number of samples, and rate equals true lambda, which is 0.2. And then we're going to carry out analytical maximum likelihood estimation for exponential. So lambda hat equals 1 divided by the mean of x. So lambda hat becomes 1 divided by mean of x. So now what we're going to do is we're going to numerical MLE using optimize. So large like becomes a function, lambda, curly brackets, if lambda is less than or equal to 0, return neg infinity. And then n becomes length of x, n times log lambda minus lambda times sum x. And then num, MLE, becomes optimize log like, comma, interval equals c brackets 0.0001, comma 2, comma, maximum equals true, brackets, $ maximum. And then the next thing we're going to do is we're going to plot the likelihood function. So lambda vals becomes sequence, bracket 0.01, comma 1, comma, link.out equals 500. Like vals becomes s apply, brackets, lambda vals, comma, log like. And then we're going to plot, brackets, lambda vals, comma, like vals, comma, type equals L, line length equals 2, color equals blue, name, which is your title, equals log likelihood function for exponential MLE, x lab, that's your label on your x-axis, equals lambda rate, y lab, that's your label on your y-axis, equals log likelihood. And then we're going to add an analytical MLE. So that's going to create a vertical line, AB line, brackets, V equals lambda hat, color equals red, line width equals 3. We're going to add a numeric MLE, AB line, brackets, V equals num MLE, comma, color equals dark green, line width equals 3, LTY equals 2. And then we're going to add a legend. So it brackets legend, brackets top right, comma, legend equals C. So there's going to be 3 lines to the legend. The first one is going to be paste analytical MLE, and it's going to be round your lambda hat to 3 points. The second line is going to be paste, brackets, numerical MLE, brackets, round MLE to 3 points. And the third line is going to be paste, brackets, true lambda equals true lambda. Color equals red, dark green, and black. So red goes with your analytical MLE, dark green goes with your numerical MLE, and black goes with true lambda. Line width equals C, brackets 331, so that's just a vector you've created. And LTY equals C, 121, and BTY equals N. So you can see here that the numerical MLE is dashed, the analytical MLE is red, and it's a straight, red and straight. The true lambda is, I think it's black and straight. So you can see that the analytical MLE is 0.191. Your numerical MLE is 0.191. And your true lambda is 2. And so you can see the chart that has been created using the MLE. So Another thing that we're going to cover is Bayesian estimation. So Bayesian estimation incorporates prior knowledge or beliefs about the parameter along with the observed data to update the probability distribution of the parameter. This approach provides a full probability distribution for the parameter, allowing for more comprehensive uncertainty qualification. And so what we're going to do is we're going to create a program in R to demonstrate Bayesian estimation. And then so we're going to use a beta binomial model. So the first thing you want to do is you want to set your seed. So every time you run the program, the variables will be initialized to the same value. So set.seed brackets 1, 2, 3. And then we're going to generate data for Benelli trials. So N becomes 20. So that's your number of trials. And your true P becomes 0.6. That's the true probability of success. True P becomes, X becomes R binom. And what that is a randomly sampled binomial distribution, brackets 1, N, true P. So that's your number of successes. And then now we're going to calculate the prior distribution being beta A, B. So A becomes 2, B becomes 2. And now we're going to calculate the likelihood binomial updates the prior. And then so posterior is beta brackets A plus X, B plus N minus X. So posterior A becomes A plus X, and posterior B becomes B plus brackets N minus X. So now we're going to plot the prior likelihood scaled and posterior. P-vals becomes sequence brackets 0, 1, length dot out equals 500. And then your prior density is prior becomes D beta. That's the density of the beta distribution, brackets P-vals, A, B. So we're going to have the likelihood scaled to fit on the same plot. So likelihood becomes D binomial. So that's a binomial distribution where it's checking the density, brackets X, N, P-vals. Like becomes like divided by max like times max prior. And then the posterior density as posterior becomes D beta. So that's the checking the density of the beta distribution. Brackets P-vals, post A, post B. And now we're going to plot all of this on a chart. So plot brackets P-vals, prior, type equals L, line length equals 3, color equals blue, Y limb equals C. That's you're creating a vector. Brackets 0, max, brackets C, brackets prior, like, posterior. Brackets, name, that's your title, is Bayesian estimation, prior likelihood posterior. So X lab, that's your label on your x-axis, equals P, Y lab, which is the label on your y-axis, is density. And then so now we're going to put some lines in there. So lines, brackets P-vals, like, C equals, color equals dark green, line width equals 3, LTY equals 2. We're going to put another line in there. So lines, brackets P-vals, posterior, color equals red, line width equals 3. And now we're going to put a legend in there. So legend brackets, top right, comma. So your legend is you're going to create another vector, and it's going to have 3 lines. So the first line is paste, brackets, prior beta. The second line is going to be paste, brackets, likelihood scaled. The third line is going to be paste, bracket, posterior beta. And then so the color on this legend is we're going to create another vector being blue, dark green, and red. So blue is your prior, dark green is your likelihood scaled, and red is your posterior beta. So your line width equals 3, LTY equals C brackets 1, 2, 1. So that means the dark green is going to be dashed, and BTY equals N. So this is the chart that we have created with this Bayesian estimation. So prior beta is blue, and you can see it's 2.2. And then likelihood scaled is x equals 1, 3. And so that's a green dashed line. And posterior is beta brackets 15.9. So you can see this is the Bayesian type of estimation. So that concludes the 3 types of estimations that I have covered in this video. So the next video is going to be another statistical topic in R, and then I hope that you decide to watch it.